Why are there so many irrational numbers? Imagine trying to measure the exact length of a perfectly round circle. You might think it's simple, but the answer is more complicated than it seems. This is where irrational numbers come into play. They are numbers that cannot be written as a simple fraction of to whole numbers. Their decimal forms go on forever without repeating a pattern. Think of numbers like pi, which is about 3.1 for 159 to 65359 to 653. Or the square root of 2, which is roughly 1.4 to 1,135,623. These numbers are fascinating because they fill in the gaps between the rational numbers, which are numbers you can write as fractions. Rational numbers include whole numbers, fractions, and decimals that end or repeat. But between any two rational numbers, no matter how close they are, there are infinitely many irrational numbers. This means the number line is packed with these endless, non-repeating decimals. The reason there are so many irrational numbers is because the set of rational numbers is countable, which means you can list them one after another. But the set of irrational numbers is uncountable, so there are simply too many to list. This difference makes irrational numbers much more common than rational ones. Many irrational numbers naturally appear in algebra and geometry. For example, when you take the square root of a number that isn't a perfect square, the result is often irrational. If you use the Pythagorean theorem to find the length of the hypotenuse of a right triangle with sides of 3 and 4 units, you get the square root of 25, which is 5, a rational number. But if the sides are 3 and 2, the hypotenuse is the square root of 13, which is irrational. Also, pi appears when calculating the circumference of a circle, and it cannot be exactly written as a fraction. In algebra, irrational numbers often show up as solutions to equations that can't be simplified to rational numbers. For example, the solutions to the equation squared equals to r plus or minus the square root of 2, which are irrational. This shows how essential irrational numbers are in solving many algebraic problems. So, the reason there are so many irrational numbers is because they fill the entire number line densely. They can't be listed like rational numbers, and they naturally occur in many geometric and algebraic contexts. Understanding these numbers helps us see that numbers are not just fractions but include infinitely many values that can't be neatly written as ratios. This idea is a key part of algebra and helps us understand the true nature of numbers.